So at this point, we've seen the Riemann integral, we've seen that continuous functions are always integrable, and we've seen, at least by example, that sometimes isolated discontinuities can be ignored. Although we didn't prove this in full generality, I think you can probably extend that example yourself to check that any finite number of isolated discontinuities can be ignored. It turns out that many other functions are integrable, and monotone functions are one of the more interesting classes. So just as a quick reminder to people who perhaps haven't seen this definition before, we say that a function f is monotonely increasing if for all x bigger than or equal to y, f of x is bigger than or equal to f of y. In other words, the function is getting bigger as you move to the right, like that. So the theorem is as follows: if f is a bounded and monotone increasing function, then f is in fact integrable. I need a little bit of notation. I define little m to be f of a, which is the smallest value of f on the interval, capital M to be f of b, which is the biggest value that occurs on the interval. And then, of course, since we're talking about Riemann integration, I need to also set a partition, and I'm going to set sort of a boring partition. I'm going to let p sub n, for a natural number n, be the partition that splits the interval ab into n exactly equal parts. So I've given a formula here, which you can check for yourself, is indeed the formula that splits the interval into n parts. Now, before giving the algebra bit of the proof, I'm again going to give a picture proof. So I'm defining, as I did in the previous few videos, a lower curve, which I'm drawing in blue. And this lower curve is just in any given interval from a to, in this case, a plus b minus a over n, that is the next point in the partition. This blue curve here is the infimum of f along that subinterval. The blue curve here in the second interval is going to be the infimum of f on that interval, and so on and so forth. So exactly like in the previous videos where I was defining integration earlier. Similarly, the green curve is going to be the upper envelope of f, that is, the green curve in this first part of the interval is going to be the supremum of f over that subinterval. The green value here is going to be the supremum of f over that second interval, and so on and so forth. And now I'm going to make an important observation for integration purposes, which is that if I look at this blue curve here, the second blue curve, it's at exactly the same height as this first green curve. Now that's not an accident of the picture. Since f is monotone increasing, we actually know that the smallest value of f on this interval is exactly this left endpoint, and the largest value of f on this interval is exactly its right endpoint. And of course, those are exactly the same points. What does that mean? Well, we notice that if we're looking at the definition of our upper bound, u of Pn, s, and subtracting off the lower bound, L of Pnf, what we're doing is we're looking at, we're adding up all of the areas of these blue rectangles and subtracting off the area of the green rectangles. Oh, sorry, the opposite of that. We're taking the green rectangles and subtracting the blue ones. And we notice that this first green rectangle exactly cancels with the second blue rectangle. The second green rectangle exactly cancels with the third blue rectangle, and so on and so forth. And so if you look at the area that gets canceled out, well, this green rectangle gets canceled once, this blue rectangle gets canceled out, and so on and so forth. The only thing that survives at the end of that cancellation is this last green rectangle doesn't get canceled out by a blue rectangle over here, and this first blue rectangle doesn't get canceled out by a green rectangle over here to its left. All right, turning that into algebra, what happens, u of Pn, f minus L of Pn, f is exactly the sum of the area of the green rectangles minus the area of the blue rectangles. Almost all of those terms cancel except for the area of this last green rectangle minus the area of that first blue rectangle. But we actually have a formula for both of these. The width of both rectangles is b minus a over n. The height of this last green rectangle is f of b. The height of this first blue rectangle is exactly f of a. And so in fact, u of Pn minus L of Pn is exactly given by this expression here. And of course, capital M, little m, b, and a are all constants, and so as n goes to infinity, this difference goes to 0. And as we saw by our integration condition at the very end of the last video, if we can check that u of Pnf minus L of Pnf is going to 0 for any sequence of partitions Pn, then in fact that means that f is integrable. Okay, so we're done. So that's sort of a cute proof because we managed to get exact cancellation. And one thing that's sort of fun here is that it actually turns out, right, it sort of matters what partition we chose. Choosing this partition meant that all of the rectangles have exactly the same width, which is what led the exact cancellation to happen. So we've seen that all monotone functions are integrable, but it's not so obvious that this is useful because we probably don't have a lot of weird monotone functions lying around. So I want to give a collection of examples of strange looking monotone functions to point out this theorem is actually telling us some stuff that isn't really very obvious. So I'm going to fix any countable subset capital D of the interval 0, 1. So this could be, for example, the rationals intersect 0, 1 in some order, but there are many, many other countable subsets, and this example is going to work for any of them. Now I'm going to define this function f of x to be a sum. It's going to be the sum over all natural numbers j, so that d sub j, that is the point in this collection of countable numbers, is less than or equal to the value x that I'm looking at, of 2 to the minus j. And I want to make a few claims about what this function f is. So the first is I want to check that it exists and is bounded. So certainly f is non-negative if it exists. But I want to point out that this function I've written down here is actually the sum over the naturals of 2 to the minus j times this indicator function here. And that's definitely summable because pointwise, we're summing something that's less than or equal to just 2 to the minus j. And we know that the sum of 2 to the minus j is exactly 1. Okay, so via some comparison theorems that we saw before when looking at sums of absolutely convergent theorems, of absolutely convergent sequences, this whole thing is definitely summable and is sitting less than 1. Okay, so we have a function and it's between the 0 and 1. I then claim that f is pretty clearly monotone. In particular, if x is less than or equal to y, say between 0 and 1, then the indicator function that dj is less than x is definitely less than the indicator function that dj is less than or equal to y for every j. So again, when you're looking at f of x and f of y, you have pairwise comparison of the thing that you're summing, which means you have pairwise comparison of the sum value f of x and f of y. Furthermore, f of x is 0 for all x less than 0, because it turns out you're summing over an empty set in that case, and f of x is 1 for all x greater than 1, because in that case you're just summing 2 to the minus j, and we know that that's equal to exactly 1. So what is the sort of the net result of all of this? We have these weird looking monotone functions, which go from 0, 1 to 0, 1, and furthermore, they're integrable, and the integral is somewhere between 0 and 1, even though it's not sort of obvious what sort of nice formula we want to be writing down for these sorts of weird looking functions. Now, it turns out these functions are not the most exotic functions that people look at, and in fact, there are functions with uncountably many discontinuities that are still Riemann integrable. We're not going to be going over any of them in this video, but I'll say that the main difficulty isn't really checking that they're Riemann integrable. The main difficulty is writing down such a function at all. These functions are all sort of weird looking objects, and it's not easy to check that they exist, that they're really functions, and so on and so forth. Okay, so we're going to be skipping it, but mainly because it's just technical to write down the examples at all. Thanks very much. In the next video, we're going to be looking at less exotic properties of integrals, for example, linearity. Thanks.